In this video, we're going to talk about the Minimax procedure and how it applies to an AI opponent. In a game such as Tic-Tac-Toe or Connect 4, there are two players that alternate turns. The first player makes a move and the second player makes a counter move. Usually as a human player, we think ahead and try to counter a move based on what we think the opponent will do next. So the problem in developing an artificially intelligent agent is how can we as programmers make a computer simulate the same forward thinking? For us humans it comes naturally, but for AI it needs to be programmed to think ahead. One way to do this is for the computer opponent to generate every possible game move from the starting move all the way to the last move, and based on this information choose the best move that will lead to a loss or draw for the human player. For games like Tic-Tac-Toe or Connect 4, searching every possible game move is feasible and doesn't require too many resources. But for a game like chess, even though there is a finite number of game moves, searching all of them would be impossible because there are more chess moves than there are atoms in the entire universe. But for Tic-Tac-Toe, the number of possible moves is under 300,000. This move list can be represented in the computer as a game tree. Each level of the game tree represents the next player's turn. As the game progresses, the number of possible moves becomes less until we reach the final game states where the human wins, loses, or draws. To search the tree and to choose the best move, we can use an algorithm called Minimax. In Minimax, the human player is trying to maximize their chances of winning, and the computer opponent is trying to minimize the human player's chances of winning. Each final game state can be assigned a value through a heuristic function, and these values can be returned to the intermediate game states. The heuristic values determine how good a possible game move is for the human player. The higher the score, the better it is for the human player. The goal of the computer opponent is to lead the human to a lower score. The human player is known as the maximizing player, and the computer opponent is known as the minimizing player. In this video, we'll walk through two examples of Minimax. In the first example, we'll search the entire game tree, which is called the Naïve Minimax algorithm. And in the second example, we'll go over a version of Minimax where we can improve the performance by eliminating searching unnecessary game states using AlphaBeta pruning. So let's go ahead and start with the first example. Okay, here's our example game tree of depth 4. The blank square nodes represent the non-terminal game positions for the maximizing player. Each max node starts with a best value of negative infinity, which is going to be the worst possible number for the maximizing player. The black circle nodes represent the non-terminal game positions for the minimizing player. The min nodes start with positive infinity, which is going to be the worst possible number for the minimizing player. The terminal game positions are the leaf nodes of the tree. These are max nodes and their values are obtained from a heuristic function. Okay, so using depth first traversal, we begin at the root node and move to the left going down. Okay, so when we reach the first leaf node, we return the heuristic value back to the parent min node. In this case, the value is 10. The parent min node applies the minimizing function to compare its initial best value of positive infinity to the return value of 10. The minimum between positive infinity and 10 equals 10, since 10 is going to be less than positive infinity. So because of that, the 10 becomes the min node's best value. This must be done for each child node. So the algorithm will move to the next node. The heuristic value of 11 is going to be returned to the parent min node, so it can be compared to its best value of 10. Because 10 is less than 11, the best value will remain at 10. Next, the parent max node receives a value from its child min node. With this value, the max node applies its maximizing function. Because the initial best value of negative infinity is going to be lower than 10, then the max node assigns 10 as its new best value. Traversal continues until the next terminal node is reached. Using recursion, the parent min node receives the 9 from the child max node. Based on the min function, the 9 is assigned as the min's node's best value, since 9 is going to be less than positive infinity. Next, the min node receives the 12 from the other child max node. Because 9 is less than 12, 9 remains as the best value for min. And because 10 is greater than 9, 10 remains the max node's best value. Next, the max node sends back to the parent min node its best value of 10. Min between 10 and positive infinity equals 10, so 10 is its best value. Now we descend to the next child max node, and from the max node down to the terminal node. The 14 is sent to the min node, and the min of 14 and positive infinity is going to be 14. The next child terminal max node, which is there, returns 15. But since 14 is going to be less, the 14 remains as the best value for min. The 14 is sent to the parent max node, and the max of 14 and negative infinity is going to be 14. From here, we descend until 13 is reached. 13 is sent to the min node, and it becomes its best value. The 14 is evaluated by the min node, but 13 remains the best value since it's lower. We return recursively to the parent max node. The max of 14 and 13 is going to be 14, so the best value will remain as 14 for this max node. And the min of 10 and 14 is going to be 10, so the 10 also remains. Then at the root node, the maximizing function is called comparing 10 and negative infinity. So 10 is going to be higher, and this becomes the root node's best value. Okay, next we explore the next child of the root node and traverse to the next terminal node. The 5 is returned to the parent min node, and the min of positive infinity and 5 is 5, which becomes the min node's best value. Next, we explore the child of the min node. We return the 2 to the parent min node. Because 2 is less than 5, the min function returns the 2, which replaces the 5 as the best value. Next, the 2 is sent to the parent max node. Because the max of negative infinity and 2 equals 2, the max node sets 2 as its best value. Next, we traverse down the tree to the next terminal node. The 4 is returned to the min node. 4 replaces the min node's best initial value of positive infinity. Next, we move to the next child terminal node. We return the 1 to the parent min node. Using the min function, we replace the 4 with 1. 1 is now the min node's best value. Next, we move back to the parent max node. The best value remains as 2 because 2 is greater than 1. At the parent min node, the best value between positive infinity and 2 is going to be 2 because it is less than positive infinity. We continue down the tree to the next terminal node. Three is returned to the parent min node. Because 3 is less than positive infinity, we set 3 as the best value. Next, we traverse to the next child terminal node. The 22 is returned to the min node. Because 3 is less than 22, 3 remains as the min node's best value. And because 3 is greater than negative infinity, 3 becomes the max node's best value. Continuing down the tree, the next terminal node has a heuristic value of 20. The 20 is sent back to the min node. 20 becomes the best value because 20 is going to be less than positive infinity. The next child terminal node has a 21. The 21 is returned to the min node. The 20 remains as the best value because 20 is going to be less than 21. However, when we return back to the parent max node, the 3 is going to be replaced by 20 because 20 is the higher value based on the max function. Now we move back to the parent min node. The min node retains the 2 as its best value. And finally, based on the root node's max function, the 10 remains as the root node's best value because 10 is greater than 2. Once all the possible game states have been generated and evaluated, the maximizing player is guaranteed at least a value of 10 by choosing the move highlighted in green. Okay, so now let's go over the Minimax Psuedocode. Okay, so Minimax is going to be a function. We call it Minimax. And it takes 3 arguments. It'll take a node. It'll take the depth of the game tree. And it'll take a Boolean value. That Boolean value represents either if it's the maximizing player's turn. If it's true, then it's max's turn. If it's false, then it's min's turn. Okay, and this function can return 3 things, right? They're all going to be. It's going to return one value, but that value can either be a terminal value. Returns terminal value. It can return the best value for min or for max, and best value for min. Okay. The next thing we'll define will be the base case. for this. Okay, so the base case. So the reason we need a base case is because the Minimax algorithm is based on recursion, right? So we need a base case in order to stop it from calling itself over and over. So if depth is 0, or the node is a terminal node, then we'll return the heuristic value of the node, of that node, right? So what if the depth, like let's say we'll call this function, and the initial call, let's say we put the initial call up here, right? So let's say we call Minimax, and we pass the first node, which is going to be the root. In our example, we use the game tree of depth 4, so we'll pass the 4 as the depth, and we'll start out with the maximizing player. So then we'll pass the value we pass there would be a true value, a true Boolean, right? So that would be true. And it's just an example. That's how we would call it, right? So initially the depth won't be 4, and it won't be a terminal node because we're starting at the root. So since we're starting with max first, then we can do another if maximizing player is true, then we'll do everything that's going to be in this code block here, right? Or else if maximizing player is false, then we'll do everything for the min node, or the minimizing player, right? Because we know that here, if this is true, then we'll use the max function here, and if it's not the max player's turn, then we'll do we'll have to use the min function. So let me show you what goes inside each of these code blocks. Right, so initially when we start, we'll set the best value for the max node. We'll set it at the worst possible value that can exist for it. So in this case, it would be negative infinity, right? And then once it's set to negative infinity, then we need a for each loop, so that way we can check the values of its children, right? So the way we would write that would be for each child of the node, then we'll execute this block here, right? So what we want is the value from the child node, but since we're starting at a max node, then the value we're going to get is going to be a value from a min node, right? So then we'll set val equal to, and since this is a recursive function, we're going to want to recall the same function, but instead of going through this block here, if we set maximizing player to false, then it'll execute the statements in this block instead, right? So minimax, the name of the function, the same name, and then we'll pass some different arguments. Instead of the root, now we're going to pass the child. And then instead of starting with depth 4, we want to start with depth minus 1. And then instead of starting with max, now we want min. So we'll set this to false. Right? So then eventually as depth decrements, eventually depth will reach 0. Or the node will be a terminal node. In that case, we'll return the value. Then once we have the value from this recursive call here, then that value we need to check it to see if it's going to be the best value. Right? So then best value, and then here we'll call the max function. The max function returns the larger number. It takes 2 arguments, so it'll look at both numbers, and then the one that's larger will be the one that's returned. Right? So it's max, and then we'll pass best value. Initially it's negative infinity, and then we'll compare that to the value we get from the child node. So then we'll compare val. And then keep in mind, once this statement runs, these 2 statements run, then it's going to have to loop again, because we have to do this for every child of the node. Keep in mind, in our example, every node had 2 children, except the terminal nodes. In real life, though, some nodes might have only 1 child, some might have 3, 4. So that's why we're using the for each, right? Because we don't actually know how many children the parent's going to have. So that's why we use for each. Okay, so then once we've gotten all the values from the children, we've run the max function, we've obtained the best value after looking at all the values, then we can return best value. Okay? So now what happens when it's min's turn? Okay, so the code's going to be very similar, right? So first of all, we'll initialize the best value with the worst possible value for min, right? Because this is min's turns now, because maximizing player is set to false. All right, so that's going to be positive infinity. So then once we set the best value for min as positive infinity, then we'll also use a for each loop, and we'll explore the children of this node. And then in this block here, we'll get the value from the child node. In this case, we're getting a value from a max node. Right? So we pass the child. The child will be a max node. Depth will also decrement to minus 1. And then here we'll set this to true. Right? So that way we know that it's a maximizing player's turn. So that way when this function is called, then it'll run this block here. Then once we get a value, we get the value from the child, then we'll determine what the best value is for a min node by using the min function. Right? So then we'll get the initial best value. Then we'll set that, compare it to val, which is the value obtained from the max node. Right? So initially we have positive infinity, but let's say we get a 10, right? So 10 is less than positive infinity, so then 10 will be the value assigned to best value. But then next we explore the next child of the node, and let's say we get a 9, right? So the best value now was set at 10, but 9 is lower, so then that value will be the best value, right? And then once we've gone through the children, exploring them, then we can return the best value for min. Keep in mind that this function will continue calling itself until this depth minus 1 until it reaches 0. In that case, all the function calls, because in recursion everything is in a stack, eventually they'll all start returning the values. Okay, now we'll perform the Minimax algorithm with the same game tree of depth 4. But this time we're also going to use alpha-beta pruning. For each node, alpha represents the maximum score that the max player can receive, and beta represents the minimum score the minimizing player can receive. The goal of the max player is to get the highest score, while the goal of the min player is to get the lowest score. Alpha and beta are initialized with the worst possible scores for each player. So alpha is initialized with negative infinity, which is the worst possible value for max, and beta is initialized with positive infinity, which is the worst possible score for min. Based on the values set for alpha and beta, we can use them to prune the branches of the game tree, or in other words, we can stop exploring the nodes of the subtree that have not been visited yet. The condition to prune is when alpha becomes greater than or equal to beta. When this happens, then we can prune. Okay, so we begin with the root node. Alpha is set to negative infinity and beta is set to positive infinity. Since alpha is not greater than or equal to beta, we do not prune. We continue exploring the game tree using depth first traversal. Each time we move downward, we pass alpha and beta. Since here alpha is not greater than or equal to beta, we do not prune. We continue until we reach the terminal node. Again here, since alpha is not greater than or equal to beta, we do not prune. And here as well, alpha is not greater than beta. Okay, so now that we've reached the terminal node, we calculate the heuristic value. The value of this terminal is 10. Next we return to the parent min node and we set its beta value to 10 because we know that the value of this node must be 10 or less. Keep in mind that the min nodes, the circles, can only modify the beta values, and max nodes, the squares, can only modify the alpha values. Also, because alpha at this point is not greater than or equal to beta, we do not prune. So we continue to explore the next terminal node. Once we reach the next terminal node, we calculate the heuristic value. We get an 11. Next, we'll backtrack to the parent min node. Because 11 is not less than 10, beta does not change, and 10 will be assigned as the value of this min node. Now we return with the 10 to the parent max node. And we set the max node's alpha value to 10 because we know that the value of this node must be 10 or greater. Because alpha at this point is not greater than or equal to beta, we do not prune. We will continue to explore while passing the alpha and beta values from the parent max node. Now we reach the terminal node, so we'll calculate the heuristic value, and we get a 9. Next, we'll backtrack to the parent min node. From here, we'll set the beta value to 9 because the value of this node must be 9 or less. Now we can see that alpha is greater than beta, so now we can prune, and we can set the min node's value to 9. Next, we'll backtrack to the parent max node. We'll set the node's value to 10 because all the children of the max node have already been explored, so we know that the 10 is going to be its best value. Next, we'll backtrack to the parent min node and set its beta value to 10 because we know that the value of this node must be 10 or less. Because here alpha does not exceed beta, we do not prune. We'll continue our depth first traversal while passing the parent's alpha and beta values. Okay, now that we reach the terminal node, we'll calculate the heuristic value. Okay, so now we get a 14. Now we'll backtrack to the parent min node. Beta does not change because 10 is still less than 14. And we do not prune because alpha is not greater than or equal to beta. We will explore the next terminal node. Perform the heuristic evaluation, and we get a 15. So now we backtrack to the parent min node. The value of the min node will be 14 because 14 is going to be less than 15. And beta doesn't change because the 10 is going to be a better value for min than the 14 or 15. Now we'll backtrack to the parent max node, and we'll replace its alpha value of negative infinity with 14 because now we know that this max node's value must be 14 or greater. Now we can see that the alpha is greater than beta, which meets our pruning condition. So we can prune and set the value of this node to 14. Now we'll return to the parent min node. Since all the children have already been explored, we can set 10 as the min node's value. Next, we'll backtrack to the max root node. We will set 10 as its alpha value because the value of this max node must be 10 or greater. Because alpha does not exceed beta, we can continue exploring. As we continue our depth first traversal, we'll pass along the root node's alpha and beta values. Okay, now we perform the heuristic calculation, and we get a 5. Next, we'll backtrack to the parent min node. When we return to the parent min node, we'll set the beta value to 5 because we now know that the value of this min node must be 5 or less. And because now the alpha has exceeded beta, we can prune and set the value of this min node to 5. Next, we will backtrack to the parent max node. The alpha remains at 10 because the best value for the maximizing player must be equal to or greater than this. Since alpha does not exceed beta at this node, we can continue exploring. We pass along the alpha and beta values from the parent max node. When we reach the terminal node, we calculate the heuristic, and we get a 4. Now we can backtrack to the parent min node. We set beta to 4 because from here we know that the value of this min node must be 4 or less. And now, because alpha is greater than beta, we can prune the remaining branch and set the min node's value to 4. Now we backtrack to the parent max node. Since all its children have already been explored, we can set the max node's value to 5. Next, we'll backtrack to the parent min node, and we can set the beta value to 5 because we know that the value of this min node must be 5 or less. And because alpha is greater than beta, we can prune the rest of the tree and set its value to 5. And finally, we return to the root max node. And since all its children have already been explored, we can set the value of this node to 10. The maximizing player is guaranteed at least a score of 10 by choosing this game state. Okay, so now we'll go over the pseudocode for a minimax with alpha-beta pruning. Right, so alpha-beta is going to be a function. We'll call it alpha-beta, and it takes 5 arguments. It takes the node, it takes the depth, it takes alpha, it takes beta, and it takes a Boolean value that's used to determine if it's max's turn or min's turn. So we'll call it maximizing player. Right? And this function, I'm going to set the, there you go. Okay. This function it's going to return one value, but it can represent either 3 things. It'll be a heuristic value from a terminal node. It'll return the alpha from max, or it'll return the beta from min. Okay? And our initial call to alpha beta will look something like this. Alright, so we call the function alpha beta. We'll pass the root node. That's where we're going to start. Our example tree was depth 4, so we'll pass the depth as 4. Remember, we'll initialize the alpha to the worst possible value, so that's going to be negative infinity. And then we'll initialize beta as the worst value for the minimizing player, which is positive infinity. And then we'll start out with maximizing player. Oh, I misspelled maximizing. Maximizing player, will initialize it as true. So we'll start off with max. All right, and then the first thing we'll need is the base case. So the base case, we'll set it here. So if depth is 0 or node is terminal node, then we'll return the heuristic value of the node. Okay, so when it's max's turn, then we're going to execute a certain set of statements. If it's min's turn, then we're going to execute a different set. All right, so we can use an if, else if for that. So if maximizing player is true, then we'll execute this code block here. Else if maximizing player is false, then we'll execute a different set of statements. All right, so let's go ahead and start with the max player. Okay, so since the max player was initialized, the alpha value was already initialized with negative infinity. Now we need to loop through the children of this node. So we're going to use a for each loop for each child of the node, the parent node. Then we're going to run this loop here. and we'll loop through the statements in this block. Right, so we want to set alpha as we go through each child. Alpha is going to be equal to the maximum between alpha itself, and since this is a recursive function, we're going to call alpha beta again. So alpha beta, and then we'll pass the 5 arguments that go here. Keep in mind that this alpha beta will either return the beta value from the min player, or it'll return the heuristic value if it's a terminal node. And then based on that value, we'll determine which one of them is greater, and then we'll assign that to alpha. All right, so here we're going to call alpha beta, but this time for the min player. So we're going to send the child. Since we're in a max node, then we know its child node is going to be a min. Depth, we're going to decrement -1. We're going to pass the alpha again. We're going to pass beta. And then this time, instead of max player being true, we're going to set max player to be false. So that way we'll run this statements here. All right, so then we'll set that to false. And then close out the parentheses. Okay, so as the loop continues running, we'll keep evaluating the max between the alpha and the value returned from this alpha beta call here until we meet our pruning condition. All right, so then that's the next thing we need to write. So each time we go through a child, we need to check if we can prune. So if you remember, the condition for pruning is if alpha is greater than or equal to beta. If it is, then we can break the loop. That'll make the that's the same thing as pruning. In other words, the for each loop will break, and we won't explore any more children nodes because we've already met the pruning condition. Once this loop finishes, then the maximizing player needs to return alpha. Right? So you can imagine when it's min's turn, min's going to return beta. So the code's going to be very similar to the one here, right? But instead, it's for the min player. Right? So here for min, so when maximizing player is set to false, then we're going to run a for each loop here as well for each child of the node. And then I'll go ahead and return this a little bit so we get a little bit more room. Right, so then now we're going to set beta equal to the min between what we already have for beta, which initially was positive infinity, and the value we get from calling alpha beta again recursively. The arguments that the alpha beta function take will be the child. Well, here we'll decrement the depth as well, right? Because we need to keep lowering the depth, subtracting 1, until we get a depth that's equal to 0. Right? So then that's the base case that will stop this this recursive function from forever executing. Then we'll pass alpha. We'll pass beta, and then this time, because this call is going to be for a max node, then we need to set this to true because it's the maximizing player's turn at this point. Close out the parentheses. Right, so then we're going to evaluate the minimum between what we already have for beta, which initially was positive infinity, and whatever this function call here returns. And in this case, it's going to return either the alpha value from max when it's max's turn, or it'll return the heuristic value of the node. Okay. Also, we need to be able, the same thing as here, we need to prune in the event that alpha exceeds beta, right? So if alpha is greater than or equal to beta, then we can break the loop, right? We don't need to explore the children anymore of the parent node, right? And then once this loop finishes executing, then we simply just return beta. Since this algorithm also relies on recursion, then we're going to be using a stack data structure. So as each function call occurs recursively, once it reaches the last function call and the base case is met, then the values that are returned from each function call will be returned to the originating function that called it, until finally the value is returned back to the main where it was initially called.